So conventionally, right, as you saw in the example, to differentiate between the parts that are being added from this and this, we put the bar on top just to differentiate between them. And then when we're using when we're expanding some of these, as you'll see in just a second, I think. So when we're expanding these infinite products, we'll put the bar conventionally over even the variable just to help differentiate between the parts and which ones are popping up. So similarly to what we did with regular partitions, we can manipulate the form of the exponent to generate certain identities or certain restrictions on the parts, the characteristics of the parts in the partition. So in this case, for example, if we set both of the exponents equal to 2k, we generate all of the partitions of an integer n in which all the parts are even, right? And this is kind of a blasé example, but it's one of the examples which might clarify how we can manipulate these exponents. So if we consider the generating function from the LZ paper, right? Remember we had, if we just basically forget about the m and the top term, we have the same generating function from the LZ paper where each of the g sub I is equal to this infinite product. Now for the overpartitions, we generalize that by multiplying it again by 1 plus q to the m. We add that additional term there with the restriction that m has to be greater than or equal to 1 because otherwise we have a 2 in the numerator and then things get ugly. So we can see that this is identical to the product side of the Gordon-Andrews identities, right? That Lepowsky and Zhu were looking to prove or work with. But the only thing is, the stipulation is there's not really any restrictions other than it has to be greater than 1 that are placed on the overline parts. So we can get basically just any overline part in the partitions, and there's no restrictions on that. So this work, as Chris Sadowski was just saying, was motivated partially by the works of these mathematicians, Corteo, Lovejoy, Mallet, Chen, Sang, and Shi. So basically, they started to study these, and we looked to further their work and generalize it more so. So we, again, considered this form, this generating function for these series, this product for these series, and we looked to find overpartition analogs to the original identities found in Lepowsky and Zhu. Moreover, we wanted to further the idea of the motivated proof, the spirit of the motivated proof, in order to just look at the product side and recuperate and recover the sum side. Okay? So, if we consider, in the case where k is equal to 2 from our original declaration of what these look like from the LZ paper, we get something that looks like this. And then notice this looks just like the Rogers-Ramanujan identities from before. And if we were to expand this, right, in a similar way to how we did before, we would have something that looks like this. So we have G sub 1 now, which was originally looked like this, and we have it expanded in such a way where now we notice that we have all of the q to a powers, the standard q to a powers that we had seen before. Just now we have this added overlined power up here. Right, and we can see when we multiply this out, we're going to start to generate partitions of an integer where now some of the powers here have an overline. So that's going to give us our overpartition, the overlined part within the regular partition. So now, if again we consider how this looks when it's expanded, you might notice that the standard division by q that we saw in the Andrews-Baxter, Lepowsky, Zhu work from before isn't going to work out quite as nicely because we had all of the original power series that are expanded here, but then we have these additional 1 plus q's to a power, right? And that's going to throw things off, and that's part of what made our work kind of unique in that the added terms in there, or the additional terms in there, kind of basically screw things up a little bit. So what made that tricky, right, like I said, is that we have to compensate for that down the line. So we have, I'm going to draw a quick picture for you to help illustrate what exactly is going on. So when we have each of the G sub I from the original Lepowsky-Zhu paper, the original Andrews-Baxter paper, We can write them out like this. We have G sub 1, G sub 2, G sub 3, and we can go all the way up to G sub k minus 1 and G sub k. So we have the series G sub 1 through G sub k. And when we noticed, or previous work noticed, that if we take the difference of these two, right, so G sub k minus 1 minus G sub k over q, right, well, I guess, okay, well, before I say that, the previous work showed that if we take the difference of these two and divide by q, we yield another series over here. And we can continue all the way down the line. Now, we want to generalize this further. This is just from G1 to GK. Right? And conventionally, the way we draw this image, right, is now we want to think about it in terms of shelves. Right? So this is our first shelf, or our 0th shelf, of our series 1 through k. So then what we want to do is we want to bump up to another set of series. And conventionally, we're going to start with GK is the first series on the next shelf. Right? And now we're just going to weave our way back this way by adding another one here. We have G sub k plus 1, right? And then G sub k plus 2. And we go all the way down until we get to G sub 2k minus 2, G sub 2k minus 1, and G sub 2k. So now...
So wait, shouldn't we start at G sub k plus 1 over G sub k?
So...
No, maybe carry it over to the...
So yeah, so the G sub k becomes the first...
Okay, so
term.
then shouldn't you have G sub 2k minus 1 as the...
Yeah.
Sorry? Oh, this, yeah. Sorry. Subscripts. So we want to know now, like, how can we get from here to here, right? And we're going to talk about that, and what we'll see is that to get from here, so this guy's the same, to get from here to here, from this shelf up to this shelf, we can take the difference of these two and divide by a pure power of q. Right? And that idea of jumping from one shelf to the next by that process was figured out initially in the works of Lepowsky and Zhu, and then was generalized by the students down the line. And we had to do something similar. So we have that picture for our shelves, right? And like I said, in terms of jumping from shelf to shelf, right, we see that this cake guy is the first one on the next shelf. And then to get from here up to here, right, we divide by pure powers of q as we had throughout the generation of the rest of these series. But the difficulty that arose with the overpartitions is that we had that additional 1 plus q to the j term, right? And to compensate for that, we had to get from here to here, right, because we had the additional 1 plus q to the j, this guy actually became a gk prime, which we basically, that was just our notation for taking the difference. Well, our gk prime was actually just g sub k divided by 1 plus q. Because we basically had to take off that extra value of 1 plus q, and then that gave us back a formal series that started 1 plus q to some power, right? And so, like I said, we take, in general, right, our primed series that starts the next shelf is the one immediately below it, divided by 1 plus q to the power. So, another thing that we had to worry about, right, is the motivation of the motivated proofs again took on this form where we're dividing by pure powers of q. That was something that was emphasized throughout all of the works from before. And because we had that additional 1 plus q to a power, we had to compensate for that throughout the rest of the proof to force this division by pure powers of q. And the way in which we did that was we incorporated, this is the ghost series. And the reason they're called ghosts, as far as I understand, is that they kind of just float around between other series. I mean, we put them in strategically, but they kind of just float around. There's a nice picture circulating with a bunch of Pac-Man ghosts that make it look fun and exciting. So, in other words, we defined these ghost series to have this specific form, right? And basically all we did, to be quick about it, is we took, in between these two series, we just incorporated a G1 tilde, right? And then in between these two series, we incorporated a G2 tilde, such that when we take the difference of G1 and G1 tilde, we can divide that by pure power of q. And similarly, g1 tilde minus g2, we can divide that by pure power of q. And we did that all the way down the line, and we defined them in this way. Now, we had to define them to be two-sided, so that way we can find an explicit formula for them, right? So that's why we have two representations. Because if we think about it as well, we're really subtracting it 2 times. We have to take g1 minus g1 tilde, and then g1 tilde minus g2, in order to generate subsequent series, right? So in general, we define the ghost to look something like this. So the initial notation, right, eliminated a lot of the subscripts. But in general, to use the Lepowsky-Zhu notation, we use all of the same subscripts as well, and then we just have this more general definition of our ghosts. And notice now, another thing to note, right, is because of the incorporation of these ghosts, right, the difference between consecutive series is, again, divisible by pure powers of q. So we've eliminated that necessity to divide by powers of q times 1 plus q to a power. So now it's just division by pure powers of q. And again, so that is important for the motivation component, right? The idea that we want to follow this structure. So the idea of ghost series wasn't uniquely ours. We kind of borrowed it from work of collaborators. So Kanade, Lepowsky, Russell, and Sills originally incorporated these ghosts into their work, and we kind of took that as well and ghostified our work. So, put all these up here. So we manipulated the equations that we had, the generalized equations for these ghosts, in such a way that we could have unique representations of these ghosts in terms of, similarly to before, in terms of series plus q to a power times another series, right? And now the only caveat is that we have this division by 1 plus q to a j because of the nature of these ghosts and how the overpartitions kind of work. And another thing to note is that at the end of every shelf, right? At the end of every shelf, in order to, again, jump from here to here and to continue the pattern of the ghosts, this guy has another ghost that pops off on the end here, which we call GK tilde. So in between every one of these series, there's a ghost series, and then at the end we have a GK tilde, another ghost that helps with the subtraction that has to occur on the next shelf, because we need that ghost series in order to continue the recovery of series down the line. All right, so by implementing these ghost series and these prime series, we were able to recover recursions similar to those found in Lepowsky and Zhu. We were able to determine that for all of the G sub I, so because now we have a bunch of different series. We have in general, we have the standard G sub i's, right? We also have prime series, G sub I prime. We have the ghost series, the standard G sub I. And then we also, at the end of every one to bump up, we had a G sub I prime tilde. So notation gets cumbersome, but we have now 4 different unique kinds of series, right? And the hope, right, it was that they all satisfy certain identities. I mean, that would be fantastic if we were getting these series that seem to mirror the previous work, and now we're getting, if we get identities to pop up, that would be fantastic. And in fact, they do, right? So if we think about the standard G sub i's that were, again, drawn from the Lepowsky-Zhu papers and just modified to overpartitions, we see that they satisfy, the overpartitions satisfy these conditions, right? So we have this this notation right here now, where each of these f sub L of lambdas, right, are just the number of L's in the partition lambda, right? So L could equal 1, and that would just be the number of partitions, the number of 1s in the partition lambda, right? In this case, it's the number of overlined 1s, and this will either be 0 or 1, because there can be at most 1 overlined part. And then another notational thing that I should point out is that we have this v sub lambda of L, and that's just the number of overlined parts. And again, that's either going to be 0 or 1. So we saw that these G sub I satisfy these conditions, right? Which are similar to the ones found in Lepowsky and Zhu, right? Similarly, for the G sub I prime guys, we have this, which again is a very similar set of conditions to the ones for the standard G sub i's, right? Similarly, for the ghosts now, they satisfy their own set of identities and recursions which look just like this. Right? And you can see that the pattern is similar. We've got the number, we have restrictions on the number of parts of a certain form, and they all are less than a value of k that is determined by the I there. And similarly, there's this congruence condition which is true to the Bressoud theorem, which titled this talk, so it had to pop up somewhere, right? So this congruence condition, basically, this is either an even number or an odd number, and these satisfy this parity condition of the Bressoud theorem. And that was true for each of the series that we've talked about so far, including this next series as well, the G sub I prime tilde, the primed ghost series, also satisfy these similar conditions. Now, the proof for the first two sets, the G sub I's and the G sub I primes, that proof is complete. We approached that and we were able to complete that proof. But for the other two series, the ghosts and the G sub I primes, their proofs are pending. But it has been verified in Maple that the ghosts satisfy the identities that we had conjectured them to have. That has been verified in Maple, and similarly we're working to verify that the G sub I prime tildes satisfy their recursions as well. And from there, we can continue to look at these proofs in such a way, and overpartitions in such a way, and recover similar identities. So, any questions?
Come on. Time for a couple of questions. So officially, you have a few more conjectures that you hope.
Yes, that is correct. Yeah. So I mean, for the G sub I primes, this is all conjecture. We still have to prove that, and similarly for the standard ghosts as well, we have to prove that as well. But the proofs should work out similarly to the ones that we had conducted for the standard G sub I's. There's just a few caveats that are thrown in because of the nature of their structure.
So you hope to prove it?
Yeah, it's a hope. Yeah, but it's a verified hope, thanks to Maple.
And are there any other extensions that you may? So this is a new proof of the criterion, or you also have new results?
So this is a new proof of the Bressoud theorems that were originally discussed in Lepowsky and Zhu.
So you have a one-to-many proof?
Yes.
Yeah.
Yes.
What
Correct.
is Bressoud's theorem?
Bressoud's theorem basically was a set of identities that were similar to this, as far as I understand, that had especially the parity condition that pops up here. Am I correct in that? Okay. Now, and to answer both of your questions as well, pushing this further, we can potentially find overpartition analogs of a number of these different theorems and partition identities that might have a similar form to this. We can find the overpartition analog for that as well.
I'll also note that the original name is overpartition Bressoud identities was given by Chen, Sang, and Shi in their paper. And the G1s and the G1, or the GIs and the G1 prime, they had a group of. The new thing is the ghosts that are helping with that, counting something.
Thanks for a great talk.